Hi, I'm Hiroyuki Goto, belonging to Disaster Prevention Research Institute, Kyoto University. I present some of soil and structure damages and the extreme ground motion during the 2016 Kumamoto earthquake, Japan. Since 14th April 2016, we have observed a sequence of earthquake events in middle part of Kyushu Island, especially in Kumamoto Prefecture. The earthquake were named Kumamoto earthquakes by Japan Meteorological Agency. The most significant events occurred on 16th April. The moment magnitude scale was 7.0. This map shows peak ground velocities observed during the main shock. The small dots shows epicenter location of aftershocks following the main shock. Large peak ground velocities were almost distributed along the aftershock distribution. That indicates the large peak ground velocities observed along the fault trace. The reason is still under discussion, but it may be a combination of directivity effect caused by unilateral fault rupture and triggering of small earthquakes. Some stations observed large peak ground velocities over 1.0 meter per second, which were 100 kinds. Kikunet KMMH16 station, operated by National Research Institute for Earth Science and Disaster Resilience, observed 1.33 meter per second of peak ground velocity. Stations located at Mashiki Town office and Nishihara village office, operated by Kumamoto Prefecture, observed 1.82 meter per second and 2.56 meter per second of peak ground velocities, respectively. Here, I show the three velocity waveforms observed at Kikunet KMMH16 Mashiki Town office and Nishihara village office. The top is east and west component, and the bottom north and south component. Every waveform shows significant pulses in east and west component. Spatial distance between Kikunet and M7.0 station is less than 1 km. They observed the common pulses in about 1 second. NVO Nishihara village office observed a clear pulse in about 2.5 seconds. The activity effect may be the major reasons of the pulse observed in Nishihara village office, because rupture process reported by several research groups indicate forward reactivity to the NVO station. I plot acceleration response spectra for the three records: Kikunet KMMH16, Mashiki Town office, and Nishihara village office. Response spectra for JMA Kobe and JR Takato records observed during the 1995 Kobe earthquakes are plotted together. Spectral shape of Kikunet KMMH16 looks similar to JMA Kobe record. Large response in 0.5 to 1.0 seconds were observed. On the other hand, spectral shape of M7.0 is similar to JR Takatori record. JR Takatori was located within the damage concentrated area during the Kobe earthquake. Therefore, significant residential damages are expected in the area. Here I note that the M7.0 record includes some effect of soil structure interaction, because M7.0 records was observed on a basement floor of the three-story RC buildings. After the cellular field surveys and reports, significant damages were concentrated in Mashiki Town. Report of Kumamoto Prefecture says a number of fatalities was 21 and a number of severe damaged houses were 2,300. There are about 30% of the total fatalities and severe damaged houses during the main shock. As I introduced extreme ground motions observed during the main shock previously, peak ground velocities over 1.0 meters per second were observed at KIC and M7.0 stations in Mashiki Town. And these response spectra are similar to JMA Kobe and JR Takatoshi records respectively. In an engineering point of view, it is important to clarify how the extreme ground motion affected the damage concentration in Mashiki Town. At this time, I cannot summarize the detailed mechanism about the issue, but I will present some information related to the topic. This is a map of damage distribution after the foreshock, 14th April. The markers here indicate a location of severely damaged houses. Estimated from aerial photos taken by Geospatial Information Authority of Japan. It was taken on 15th April. That was the one day before the main shock. And this is a map of damage distribution after the 16th April. Obviously, a number of damaged houses increases, and the damaged area expanded. I show some typical patterns of damages in Mashiki Town. Some of the damages, especially eastern side of the damaged area, were induced by building land. In the area, there are complex topographies and artificial landing was required. So, I cannot estimate the age of landing. On the other hand, some structures might be damaged by strong ground motion itself. The steel frame building here was severely damaged. The second floor was crushed. Note that the damages were concentrated on modest ground slopes, not on a flat land. Kikunet KMMH16 station, observing the large ground motion, is located outside the damaged area. The damage surrounding the station was relatively moderate. On a flat land in both sides of Akitsu River, less residential damages were observed. On the other hand, some significant ground damages were recognized in the area. A typical example was damages on river embankment. At this time, the reason of damage contrast is not clear. I will point out some evidences to help the discussion. The one possible reason is the vulnerability contrast of the structures. The backgrounds are aerial photos taken in 1964 and 1986, respectively. The damaged area is well correlated to the town established by 1964. On the other hand, some houses seen in the outside of the damaged area in the aerial photo taken in 1975. For the Japanese standard for architecture buildings, new building code published in 1981 is important. This implies that some houses outside the damaged area were not constructed under the new building code, and the houses should be also vulnerable. It seems not to be simple. Another possible reason is the surface faulting in the area. Geological Survey of Japan reported the distribution of surface faulting caused by a sequence of the earthquake. They reported that over 2-meter surface faulting was observed in Dawson district after the main shocks. However, in the damaged area, some surface faults were recognized, but there are no significant faultings compared to the Dawson area. The faulting might cause the structure damage locally. More evidences are required if the damages in Mashiki Town were caused by the faultings. The third possible reason is the difference of ground motion. This shows damage distribution overrides VS30 map available from Japan Seismic Hazard Information Station. The damaged houses were distributed on 200 to 300 meters per second of VS30. The contact patterns of VS30 seems not to match the damage distribution well. Notice that the VS30 values are roughly estimated from the site classification by geomorphology. Therefore, it is required to clarify the actual site amplifications by conducting geophysical surveys and temporal observation of ground motions, or another information required. A remarkable evidence may be derived from the ground motion records observed within the damaged area. Hata et al. Succeeded at observation during the main shock, and the records directly show the larger ground motion than KICNET KMMH16 records. The detailed reports will be available soon. That is all my presentation. Thank you very much.